Do you have any questions about addition of asymmetrical addition of HCl to asymmetrical alkene? When HCl is being added, so you have addition of H first, and then carbocation forms. The first carbon, the second carbon will take the plus charge. So just know that, because when H plus comes in, does not bring any electrons. And in order to form that new bond between H plus and the carbon, you do need pair of electron. So pair of electron from the pi bond is going to be consumed to form that new bond between hydrogen and carbon. For carbon 1, basically, there is no difference in terms of number of electrons. So if I expand this, say if you have a CH3, CH, then you have your CH2. The new hydrogen that is coming is going to take the pi electrons to form the new bond. Now you count the number of bonds for carbon 1, you have 2, 4, and then 4 electron used to attach to the hydrogen. So if you would expand this hydrogens, you can put them in like a loose structure format, like open. So you have your all bonds shown. So you have your 8 electrons. I just want to emphasize why the other carbon takes the plus charge. So you have your 8 electrons for this carbon. The other carbon has bond to one hydrogen, has bond to one hydrogen. If I show the bonds, have one bond to the hydrogen, one bond to carbon on the right side, and one bond to the carbon on the left side. So there's only 6 electrons for this other carbon 2. So carbon 2, as a result, is going to take the plus charge and is the carbocation that forms. So if carbon 1 gains the hydrogen, carbon 2 takes the plus charge. If carbon 2 takes the hydrogen, carbon 1 takes the plus charge. So since it's a primary carbocation is very unstable, is not going to form. But for the secondary carbocation, is going to, of course, more stable, and it's going to form, and your major product is going to be 2-chloropropane. This addition, when it happens with this manner, that hydrogen is added to carbon with greater number of hydrogen, and the nucleophile or the Cl is added to the hydrogen with least number of, is added to the carbon with the least number of hydrogens. It's called Markovnikov addition. So we have Markovnikov addition there. We looked at the other examples. These are kind of repeated from before. You have a major product, minor product. When you're adding HI, hydrogen will add to the carbon with more number of hydrogen, and the iodine would add to the other carbon. That would be the major product. In this case, hydrogen is going to add to this carbon because it already has one hydrogen. So hydrogen would add to the carbon with more number of hydrogens, and Br would add to the carbon with least number of hydrogen, and that would make it major product. So we are getting highly substituted alkyl halide. So this is again is known as the Markovnikov product. The other product is counted as the second, as a minor product, because the carbocation that forms is a secondary. We saw in previous example that if it's a primary carbocation, it doesn't even form. So, any questions about the Markovnikov rule? The electrophile would add to the carbon that is bonded to greater number of hydrogen, and the nucleophile is going to bond to the carbon that has least number of hydrogens. Questions? Okay. So based on the Markovnikov rule, addition of proton to a double bond or carbon-carbon double bond of alkene results in a product with the proton being bonded to the carbon that already holds greater number of hydrogen. So that's known as the Markovnikov. Or you can say that it will add in a way that is going to create a more stable intermediate or more stable carbocation, or more stable intermediate. That's more better term because it's going to cover all other intermediates like a free radical as well. We talked about these already. Do you have any questions? Is
there a case where you'll have equal number of hydrogens on each carbon in the...
If you do have equal number of hydrogens, then you will get like a 50-50%, but you will get a mixture of
racemic
products. Yes.
Gotcha.
Very good. So what would be, for the retrosynthesis, what is retrosynthesis? You start from product, and then you predict what would have been the reactant in order to make this product. So if you're adding HBr, H should add to carbon with greater number of hydrogens, and Br should add to carbon with the least number of hydrogens. Or if this is the case that both of them are the same, then you want to see which is going to give you better or more stable carbocation or intermediate. So if we already know the location for Br, we have two choices. The carbon-carbon double bond would have been on the carbon that carries the Br with the carbon on the right side, or the carbon that carries the Br with the carbon on the left side. So basically 2-hexene or the 3-hexene. Which one would be better? Would it make any difference? Which one would be a better choice in this case?
Would it be the 3-hexene?
Why would what makes the 3-hexene to be better?
I just kind of looked at the symmetry.
Mm-hmm.
I don't think it matters since they have equal number of hydrogens, right?
They have equal number of hydrogens. So if you take this and you add HBr, let's see what are the products. One of the product is going to be Br attached to carbon 3 and then H attached to carbon 4, right? The other one would be from the other side. So you would get the Br on carbon number 3 from the left side, and then hydrogen to the carbon 4. Either case, you would have 3-bromo. Right? In either case, you would have 3-bromo hexane. So this way, you don't have any impurities. It would be just one single product. When you have single product, you don't have to worry about like purification. You don't have to worry about byproducts. If you have two, you add HBr. If we take the statistics and we say both of them say they have same number of hydrogen, then which one would be better choice? So you could have carbon-carbon, if Br adds to third carbon, that would be one choice. That means that hydrogen added to the second carbon. The other one is going to be Br added to the second carbon and hydrogen being added to the third carbon. So it's going to have a major and minor product, because 3-hexene is going to give single product. It's going to be better choice. Okay? Now, if you have this, which one is going to be major product, which one would be minor product? You're going to have a mixture of the two, because both of them, there is no discrimination. You have a CH and CH. There's no major minor. So you would have a mixture of the product. Now, which one would be slightly more? Well, if we try to say like which one is like slightly more, in this case, you have ethyl group, and then you have like a propyl group. In if the carbon 2 is positive, you have a methyl group and then butyl group. You still have 2 groups. So it's going to, maybe this would be better choice. Maybe the addition of the Br to the third carbon is going to be better choice, because in this case you have a methyl and then a butyl. But it's not a solid answer there, because both of them, they have same number of hydrogen, and both of them is going to happen. Like both addition could take place. So this is just that's on the next slide. It's just explaining that if you have the 3-hexene, you would get single product, and because it's a single product, there is no discussion, and it would be better. Now, if you have Markovnikov addition, what would be anti-Markovnikov addition? In the anti-Markovnikov addition, electrophile or hydrogen will add to carbon with least number of hydrogen, and the Br would add to the other. So it's the opposite to the Markovnikov product. How can we get anti-Markovnikov product, or how can we induce formation of anti-Markovnikov product? We have to change the mechanism of the reaction. And if you change the mechanism for the reaction, you get the used intermediate. If it's a free radical, change reaction. So instead of bringing the HBr first, you are going to bring something that is going to create a free radical. Still, the idea is to have the most stable intermediate. So that's why last class I was emphasizing on basically, formation of the intermediate, and how stability of the intermediate is going to yield major product. Is the same idea, and the only difference is that in anti-Markovnikov you have formation of free radical. In Markovnikov you have formation of carbocation. So when you have the formation of the free radical, basically instead of hydrogen coming in first, instead of hydrogen attaching to the carbon-carbon double bond, now it's going to be Br. And since the cleavage is going to be hemolytic cleavage, you are going to get Br free radical. So your Br free radical is acting as electrophile, and the Br free radical is the one that is going to react with the carbon-carbon double bond. And when it does react with the carbon-carbon double bond, you are still looking for the most stable free radical. So in this case, if Br attaches to the carbon that has more hydrogen, to this carbon, the carbon with least number of hydrogen, or the carbon that is more substituted, is going to take the free radical. So basically you have here a tertiary free radical. If Br attaches to the second carbon, so if you basically had the CH3, Br, and then CH3, the CH would have been free radical, and this is a secondary free radical. When you have like a secondary free radical, tertiary free radical is more stable than secondary free radical, and as a result, we can see that Br, free radical, is going to attach to a carbon with greater number of hydrogen. This does not follow the Markovnikov rule, but the product that is, or intermediate that is forming, is going to be more stable because it gives us tertiary radical and is more stable. This product is known as anti-Markovnikov product. For anti-Markovnikov product, hydrogen would add to carbon with least number of hydrogen, and Br would add to carbon with greater number of hydrogens. So if you learn about one and you learn about the mechanism and know the facts that if you have more stable intermediate is going to give you or yield to major product, those are the fact that you need to memorize it, you need to know it by heart. And the rule for Markovnikov and anti-Markovnikov is just that is going to help you with like expanding your knowledge to other reactions. But what doesn't change is the rule that the tertiary carbocation is more stable than secondary carbocation, more stable than primary, and primary carbocation doesn't form because it's not very stable at all. But the other fact that the more stable intermediate yields major product, and also tertiary free radical is more stable than secondary free radical, more stable than primary free radical. So based on the difference in the stability of the tertiary, which I had it already, the explanation, I just showing also in this slide, is that secondary is less stable than the tertiary, and this is the one, because it's less stable, it doesn't yield to formation of product, or if it forms, it's going to be the minor product. Questions? Okay. If the addition of water, that's this reaction is called hydration. If you remember from the first table that we had, hydration, hydrogenation, and I talked about is you're adding H plus and OH minus. So since you're adding H does not change the functional group, but since you're adding OH, the product is going to be alcohol. The other problem is, or the fact is, that if you add water with alkene, they are not miscible, is not going to even react, or alkene, like oil, does not dissolve in water. So they have no interaction. It is not going to dissolve or react with it. So you have to do a acid-catalyzed addition of water. So you bring H2SO4 as the catalyst. So you bring sulfuric acid, add drops of sulfuric acid as the catalyst. It's going to generate or dissociates to HSO4 plus H plus. So it dissociates. The H plus then is going to react with the alkene first. So, or the alkene, if you go from electron rich to electron poor, the carbon-carbon double bond is going to attack the H plus, or you can say that alkene is going to be protonated. And as soon as alkene is being protonated, it's going to form carbocation. So when alkene is protonated, okay, you have carbocation. Now, carbocation is so reactive that doesn't look for the water to be reactive or not. Even though water is not very strong, electrophile or nucleophile, is going to is going to react with carbocation because carbocation is very reactive. So you only need one species to be very reactive. If you remember from 1046, when you do acid-base, if you have a strong acid, it's going to react with weak base. If you have a strong acid, definitely would react with strong base, but if you have a strong acid, it would definitely react with weak base, or a strong base can react with weak acid. It doesn't matter if the acid is strong or weak, as long as you have one strong item there. If you have a strong base, it would react with strong acid and weak acid. So in this case, you are first using a catalyst of sulfuric acid to change the alkene to carbocation. And then the carbocation is going to react with H2O. H2O has pair of unshared electrons. Pairs of unshared electrons that you have on H2O, it makes it nucleophile. The nucleophile is going to look for the nucleus, which is the carbocation, and it's going to form bond. So basically, it's going to use pair of electron from the oxygen to form bond with this carbocation. It's going to be on the next slide, so I don't want to write everything and then bring the next slide. By the way, end of the class, remind me about 20 minutes into the class, I want to talk about the exam. Today, I will talk about the exam, so don't leave, make sure that you're there when we are talking about the next exam too. But first, I want to finish the lecture. Okay, on the first step, you get carbocation, formation of a carbocation. And second step, which is the fastest step. Why is the fastest step? Because you already have a carbocation that is very reactive. It's going to react with the nucleophile or water, and is going to the water is going to attach to carbocation. Pay attention to the charges. You have a plus charge here, and water is neutral, no charge. Okay, there is no charge on water. So if you had like a Br minus, what would have happened? If you had a Br minus, it would have come in, Br minus with the C plus, it just forms a new bond, and then you don't have to worry about a plus charge. But if your nucleophile is a neutral compound, and you do have a carbocation, when you bring a neutral plus a plus charge or carbocation, what happens to plus charge? Is plus charge being canceled or not initially? See that when water attaches to carbocation, this plus charge is not going to be canceled. The plus charge is there and it's on the oxygen, because oxygen is the one coming to rescue the carbocation or to react with the carbocation. So the plus charge is going to be shared between carbon and oxygen, and is going to make this molecule, is not a molecule, is basically intermediate, because if any species has charge, we cannot call it product or we cannot call it molecule. It's intermediate still. It has a plus charge on it. It's very unstable. Why is unstable? Because oxygen does not like the plus charge. So what would be solution? The solution would be, if you remove one hydrogen as a H plus, basically you are removing hydrogen with the plus charge. So anytime you have OH2 with the plus charge, you have to do one of these two, either remove hydrogen with the plus charge. So this base or water or the solvent acts as a base and removes the hydrogen with the plus charge. And then you end up with OH only. So OH is left. So you are removing H plus using the solvent. The other solution, which is not going to benefit here, is to remove H2O and then leave the plus charge. A plus charge on carbon is a lot more stable than the plus charge on oxygen. Oxygen doesn't like to have the plus charge. But if we remove water in this case, it's going to go back. We don't want to go back. We want to go forward, and we want to make alcohol. So we use water to remove hydrogen from this intermediate. So you remove the H plus, you're taking care of the extra hydrogen that is there. You're also taking care of that plus charge that is on that intermediate. then you would have your final product as alcohol, final product. So what is the net result of addition of or acid catalyzed addition of water? The net result is formation of alcohol, or the net result is addition of water. So if you have CC double bond here and you want to add water, H2O, you have to use acid catalyzed. So when is it catalyzed, or is it you are using catalyst? A catalyst is not consumed in the reaction. It's going to be consumed and then it will be reproduced. Catalyst is something that it enhances the reaction. It would help the reaction to happen, but is not consumed in the reaction. It's just like enzymes. So when you are using like sulfuric acid, the sulfuric acid is not going to be consumed in this reaction. It would just is used temporarily and then it will recover it. The net result is addition of H and addition of OH. H is going to add to carbon that has more hydrogen, and OH will add to the carbon that has less hydrogen. So basically, you would get the OH on second carbon. This addition is Markovnikov addition. How do we know it's a Markovnikov addition? Because you have a carbocation intermediate. So you could also remember that this reaction is a addition of water, or acid catalyzed addition of water is going to be Markovnikov addition. The net result is formation of alcohol. The direct addition, this reaction also known as direct addition of water, okay? Direct addition of water. Another example of acid catalyzed addition is addition of alcohol when you are using acid as a catalyst. So your catalyst is going to first protonate the CC double bond. Which double bond is going to be protonated, or hydrogen will add to which of these two carbons from carbon-carbon double bond is the one that would give us best carbocation. So if the hydrogen comes and protonates the first carbon, the second carbon will take the plus charge and you're removing the pi bond. Then the nucleophile, which is the alcohol, is going to then attach to the carbocation. So the nucleophile, when it attaches to carbocation, again is a neutral nucleophile. Because it's neutral, the plus charge is not going to go away, since it's going to stay there. Since the plus charge is on the oxygen, is going to make this molecule very unstable. And since it's going to be unstable, you have to do something to it. You have to remove a hydrogen with the plus charge, and the net result is going to be, so how to remove the hydrogen? You have to bring a base. Now, this hydrogen, removing of this hydrogen with plus charge is so beneficial to this molecule that is going to, it's very easy to remove. It's very easy to remove, and even just the alcohol or water can remove this hydrogen with the plus charge. So the net result is going to be addition of H to one carbon, addition of OR to another carbon. So when you write the general formula for alcohol is ROH. When you are adding ROH plus CC double bond, H is going to add to one carbon and OR would add to another carbon. So you're going to have COR. R represents what? What is R? R is alkyl group, right? Whatever it is going to start with a C. So you're going to have CCOC. It could be one C or more than one C. It could be like a methyl group or it could be ethyl group. But what's this functional group is ether. So we have ether. You start with alkene and you change that to ether. So what you need to know, addition of alcohol to alkene, the net result is formation of an ether, that's ether. This reaction, because you don't have a strong acid or electrophile here, because you have to first add the electrophile, because it's not a strong electrophile, like water is not strong electrophile, you have to use a catalyst. The catalyst that you are using is H2SO4. A carbocation is going to form first, and then alcohol would add to the carbocation, and you have to remove a hydrogen. Removing of a hydrogen, we already saw it in addition of water and addition of alcohol, that because alcohol and water, they are both neutral and you're adding to carbocation, it cannot cancel the plus charge. So the plus charge is going to stay. And since it stays, you have to bring a solvent or your nucleophile to get the, to remove the hydrogen with the plus charge. Any questions about addition of water or addition of alcohol? Is this Markovnikov addition or anti-Markovnikov addition?
It's Markovnikov.
Is Markovnikov because, again, is an acid-catalyzed reaction and you're getting the carbocation formed first. When you have carbocation forming in a chemical reaction, when the mechanism shows that carbocation has formed, there is one problem or disadvantage, and that is rearrangement of the carbocation. So when carbocation forms, and in order to see this, you have to, if this is like question, you have to make sure that you are going to draw the structure formula for this molecule, and then you can see, is there a possibility for rearrangement or there is no possibility for rearrangement? Because from molecular formula, it's very hard to see you have carbocation rearrangement or there is no carbocation rearrangement. So on the first step, when you have hydrogen coming and forming bond with one of these two carbons, is going to be Markovnikov rule, because we are bringing H+. Since you bring H+ as the electrophile, we know that is going to follow the Markovnikov rule. So based on the Markovnikov rule, a hydrogen will be attached to this carbon, and the carbon adjacent to that would take the plus charge. And if you classify this, what is it primary, secondary, or tertiary? What type of carbocation do we have here?
Secondary.
This is a secondary. If rearrangement wants to take place, for the rearrangement, have we talked about rearrangement already in this class or no?
Yeah, I think we always want a higher. Tertiary is like.
Yes, we are looking for a higher order, more stable, based on the stability of the carbocation. Tertiary is more stable than the secondary, more stable than primary. If you have a primary, it would definitely look into changing to secondary or tertiary. And the chances that you have for rearrangement would be based on the methyl shift or hydride shift. Hydride shift is easier because when you do hydride shift, you're only taking hydrogen with 2 electrons. When you do methyl shift, you have to take the CH3 group, and a hydride is smaller than the methyl. As a result, a hydride is easier, but there is no hydrogen on this adjacent carbon. You do have, however, you do have a couple of methyl groups. If you take the methyl from the carbon 3 in this case, and then you move it to carbon 2, you are taking the electrons with the methyl group. So you bring the electrons, pair of electrons. If you bring the pair of electrons, the carbocation gains pair of electrons, so the charge would go away. You see here, there's no charge on this carbon, but the carbon that is losing methyl group with the pair of electron now has only 6 electrons. As a result, you would get that plus charge. So if you shift the methyl to adjacent carbon, you are going to transfer the plus charge. Basically, you're switching the methyl group with the plus charge. It's called the methyl shift. So it gives you like a tertiary carbocation. And if you have a tertiary carbocation, is more stable. So your final product basically is not what you would expect simply by adding H2 to following Markovnikov rule, adding H to first carbon because has 2 hydrogen already, and Cl to second carbon because has only one hydrogen. So you would see a rearranged product, and that would be the major product. And why is major product? You would have this minor product, but why is this major product? Because tertiary is more stable than the secondary. Let me know if you have any questions before I go to like next example. Okay, if you don't have questions, the next example is very similar to what we had before. In this case, H plus is used as electrophile. So if H plus is as electrophile, I'm repeating. So hopefully that would kind of registers with you also. If you add the H plus, the reaction is going to yield a Markovnikov addition. So the addition is going to be Markovnikov. You're bringing H plus as the electrophile. It's going to add to carbon with the higher number of hydrogen. The other carbon will take the plus charge. And we have a secondary in this case. If you have a secondary, then we have the carbocation has formed and it is secondary. Okay. If carbocation formed and it was a tertiary, we would just stop there. There is no rearrangement. There is no benefit for rearrangement. Why would it go from tertiary to like secondary or primary? But if the carbocation is primary or secondary, then you look around on the adjacent carbon. Is there a possibility for rearrangement to go higher order or not? So if you look at this molecule by hydride shift, you can switch the plus charge with the hydride group, and then you end up with a tertiary carbocation. So this 1,2 hydride shift is going to take place, and you have a tertiary carbocation, and that would yield major product because tertiary carbocation is a lot more stable than the secondary one. So 2 possibility, hydride shift or methyl shift. If, like for the example that we had earlier, if instead of these methyl groups, they were all ethyl groups, then there was no chance for rearrangement because you didn't have methyl group on the next carbon and you didn't have hydrogen on the adjacent carbon. So if you had only ethyl group attached to this carbon, then you would have no chance for rearrangement. The molecule had no chance for rearrangement.
Would it matter which methyl group shifts?
No. It's a sp3 and they're all equal.
Okay.
Yes, it doesn't matter. Okay. If the carbocation that forms in this case is going to be secondary carbocation, should we see any rearrangement? Is there a benefit of rearrangement? If it wants to form a rearrangement, the carbocation can go to the first carbon, which is primary, is not going to happen. It can go to the one on the left side by hydride shift, then it goes from secondary to secondary. So secondary to secondary, it's going to be, there would be no benefit because it doesn't add stability and it's not free of energy. So the rearrangement, it only takes place if there is a chance on the adjacent carbon only, either on the left side or right side. This methyl group or the hydrogen that we have is 2 carbon away. So there is no way that you can bring the plus charge here to make like a tertiary. Whatever is going to happen is going to happen only by 1 bond difference. So either on the left side or the right side. And there is no benefit here to go from secondary to another secondary. There is no benefit. So there is no chance for rearrangement. So this could be an example, like in a slide, but on the multiple choice questions, you would have this one and the 2 examples that you had before. And the question is, which compound there's no chance for rearrangement. Then the only way that you can answer the question correctly is if you had enough, like, you looked at the structure and see this double bond is 2 carbon away from the tertiary. And because it's 2 carbon away from the tertiary, then we don't have a chance for rearrangement. And when the secondary forms, there is no way that it would go to primary. So no chance on this side and no need for on the left side, because it goes from secondary to secondary. This rearrangement, it can be so strong or so highly favored that can even open a ring. So when you see this example, how could this happen, is just it is more of like an explanation that a carbocation is going to form first, and this carbocation is going to have a shift in a way that it opens the ring. So it's the 1,2 is a metal shift or ring expansion. So it's called the ring expansion. So when would this happen? Ring expansion only happens if when you bring when you open the ring, there is a branch already there, and the secondary carbocation is going to change to a tertiary carbocation. So you have a secondary here. This is a tertiary. If there is no chance for no chance for upgrading, carbocation is not going to happen. The angle of strain here is 90, or the angle is 90 degrees for sp3 hybrid. The sp3 is supposed to be 109.5, and it is actually 90 degrees, because we all know from math class that a square has 90-degree right angle all around. But in this case, for a pentagon, the bond angle is 108. So the angle of strain also is being reduced. And I remember your class had the questions about which cyclic systems they are the most stable, and we did talk about cyclopentane and cyclohexane being the most stable cycloalkane. So cyclobutane is unstable, so it's going from unstable to stable ring, and is going from secondary carbocation to tertiary carbocation. So these are the 2 factors that is going to affect or help the ring expansion. Otherwise, you don't break the carbon-carbon bond. And so every time you do have carbocation formation of carbocation, you look for the possibility for rearrangement. Next type of reactions. I said beginning of when I start covering chapter 8, I said a lot of reagents that you have to memorize. And most of the reactions, 90% of the reactions, they are addition reaction. You are breaking pi bond, forming 2 sigma bond. A electrophile would add first, and then the nucleophile would add second. So that's like a general. But what is different from one reaction to another reaction is the reagent that you are using, and then is the arrangement. So for every specific reaction, you need to know, is this Markovnikov? Is it anti-Markovnikov? It doesn't make the difference. So there is no Markovnikov, anti-Markovnikov. And the addition is going to be syn addition or anti-addition. So when we say like a syn addition, that means both of them are added from the same site. If you say anti-addition, that means one group is added from the top, one group is added from the bottom. And with the examples, you could see that if carbocation forms, what would be the case? Is it syn or anti-addition? If carbocation forms. Let's say I have a carbocation here and I bring a Br minus. And I have the hydrogen here that was added earlier. Would this Br add from the top or would add from the bottom? A or B? So if it adds from the bottom part, since already hydrogen is being added here, is going to be known as the syn addition, same side addition. And if it comes from the top, is anti-addition. What do you think will happen when there's a carbocation, formation of carbocation?
I think the syn addition.
When you have carbocation, that means you have sp2 hybrid. Carbocation is a sp2 hybrid, okay? And you have a sp2 hybrid with the unhybrid p orbital. So it's going to be basically 50%, 50%, the top and the bottom. That's when you have carbocation, formation of carbocation.
Okay.
So if it's a carbocation, it would be like 50-50. That's why so far, when we were talking about, if it's like open carbocation, there is a carbocation here, we do have the plus charge, but is restricted. But if it's open carbocation like this, with the sp2 hybridization, then the addition could be 50-50 from the top or the bottom. So that's why with all the reactions of addition of HCl, HBr, H2O, and alcohol, we didn't say anything about syn addition or anti-addition. But when it comes to like addition of Br, now we see that it's going to be more specific, and the second Br cannot come from the same side that the first Br came, so it must go from the other side, and we learn about the anti-addition from in this slide.
That's for
So-
all halides, right? Not just Br?
Yes, for all halides, or is going to be for anything that has a triangle carbocation with the restricted carbocation with a triangle. That's going to help you more because it would be less to memorize. Anytime you have a intermediate that forms a triangle, the addition is going to be anti-addition. So addition of Br2, is this Markovnikov or anti-Markovnikov? What about addition of Cl2? Markovnikov or anti-Markovnikov or neither?
Neither?
Neither, because you have Br, the first Br added to one carbon and the second Br added to the other carbon. So there is no discussion about Markovnikov or anti-Markovnikov addition. When you're adding H2, it's the same thing. Hydrogen is added to one carbon, the other hydrogen is added to the other carbon. So there is no Markovnikov or anti-Markovnikov discussion. But what is discussed here is the formation of this intermediate. So the pi bond is going to form bond with the first Br, and the second Br is kind of it's going to leave with the pair of electron. Since the second Br is leaving with pair of electron, that means the Br that was coming or forming bond with this double bond, it's plus charge, it's positively charged. So it's going to bring the plus charge into the ring. And based on the mechanism, is going to, or based on what it shows in here, a triangle is going to form. It's going to be easier for you to say that triangle is going to form and learn about that when there is a halogenation. This reaction is halogenation or addition of halogen. A triangle is going to form, then discovering why a triangle is going to form. Okay, why a triangle is going to form, you can learn that in graduate school. Just don't go there because you don't want to add too much to your plate. But a triangle is going to form. It's going to bring in the plus charge. So this plus charge is going to be basically distributed among the carbon, and Br. Is not going to stay just on that Br. but the plus charge is going to come into the ring. Then the other nucleophile or the bromide with the negative charge has two choices to go from the top or from the bottom. Which one is preferred? Because the top is already, there's already BR there and it's restricted. It cannot go from the top, it's going to come from the BR. So when come from the bottom. So when it comes from the bottom part, this triangle, remember the angle strain is a triangle. sp3 hybridization is like a 60 degrees. So it's going through a lot of pressure and strain. It's easy to break this bond here. So when the BR comes in to form bond with the one of the two carbon, because it's symmetrical, it doesn't matter which carbon is going to take the BR. When it comes in, is going to break the bond for the triangle, and it would you know, you have the BR, because there is a minus charge coming in, is going to cancel the plus charge as well. The reason why this bond is going to break, count the number of bonds this carbon has already. How many bonds this carbon has already? I'm talking about the carbon that is
4.
taking the BR. Already has 4. And that is the maximum number of bonds for carbon, cannot take 5 bonds. That's the reason as soon as the Br minus comes in and forms bond with the CH2, the bond from the triangle side is going to break over the Br. It's going to take the electron goes in and cancels the charge also. So a lot is happening here, but you have learned the basics already. That's why we don't have to go through all that again, because you already know that if you have a negatively charged nucleophile coming in to a carbocation or intermediate that has a plus charge, you don't have to worry about further action, because the minus and the plus is going to cancel each other's effect. We already know that there is a triangle here with a 60-degree angle strain is very high, the pressure is very high, and is ready to break this triangle. So it is beneficial. And also the addition here is the anti-addition or anti-addition. And in the anti-addition, one Br is added then from the top, and the other Br is going to be added from the bottom. For this molecule, it would not make a difference because each carbon has a 2 hydrogen. There is no chirality there. But if there was a chiral center, then we had to worry about, you know, which one is coming from the top, is coming from the bottom, how is going to affect the stereochemistry of the molecule. But in this case, it's just the theory that just the fact that there is a triangle already on the top part of the molecule. So for the bromide to come in from the bottom part, it's going to be much easier. Now, the other question is, with this bromine, the bromide, is it going to attach to carbon on the left or would it attach to carbon on the right? The answer is it doesn't matter. It is symmetrical. It doesn't matter. But if you had a case that it was a, and since it's like BR is not going to make a difference. But if you had, again, a chiral center, when there was a chirality in the molecule, then we had to worry about and make sure that we know, you know, which carbon is going to take the second bromine. Okay, a lot of information, but just take one reaction at a time. Please make flashcard. There are a lot of reactions in this chapter, and know the reactions by the name. So you need to know hydration. For hydration, we have 3 types of reaction. It's called direct hydration. That's the one that we already talked about. And that is the acid-catalyzed hydration. So you have oxymercuration, demercuration, hydroboration, oxidation. Those are only hydration. And you have halogenation. You have addition of HX. You have addition of alcohol. So for each one, you want to know if the product is going to be Markovnikov, anti-Markovnikov, or neither. If the carbocation intermediate forms, then there is no question about is it going to be anti-addition or syn addition. But if you don't have a open carbocation forming, then if a bridge forms or a triangle forms, then you want to know if the addition is going to be anti-addition or a syn addition. Is there a chance for rearrangement? If there is a chance for rearrangement, let's say if you have you bring the chlorine first and you get the triangle here with the chlorine, and then the other chlorine comes in. Is there a chance for rearrangement? I give you the answer. Whenever you have a restricted triangle, the plus charge is not moving. So there is no chance for rearrangement. So when you see this triangle in the formation of the carbocation, so your carbocation is not like an open carbocation, is restricted. The plus charge is shared within the triangle or a bridge. There is no chance for rearrangement. So the product here is going to be, one chlorine would be added to each, one chlorine would be added to each. So there is no chance for rearrangement, or bromine would add to the.
Just a question, what about for cyclohexanes or benzenes? Would the same apply for them?
Yes, same for apply. Let me see. Okay. Let's say you have a cyclohexene. Okay, you have a cyclohexene and you want to add a Br2, then the product is going to be Br and then Br, like that, anti-addition. Is that what you mean? Is it going to be? Yes, it's going to be anti-addition, one top, one bottom. And then if you draw the like a cyclopentene like this, you should go like Br up, Br down, like that, or use show that is anti-addition somehow. Okay, next. Okay, halohydrin. For addition of the halohydrin, you're adding Br2 and you're adding H2O. You add the Br2 first, or you add the Cl2 first, and then you add the H2O. So it's like a halohydrin. So in this case, you are going to get the, so go with the order. Since you're adding halogen first, you see that for halogen, you didn't have to use catalyst, right? But for water, you had to use catalyst. So if you're adding both of them, which one is going to come in first? Is going to be the halogen that coming in first, because halogen doesn't need the catalyst. So when the halogen comes in, it's going to form that triangle. Okay, so you have the triangle when Br2 comes in first, then the OH comes in, or H2O would come in. H2O is neutral, there is a plus charge. So this involves a additional step because H2O is neutral and the plus charge is not going to go away. It's going to stay on the H2O. Then you have to remove a hydrogen with the plus charge. Now, which carbon is going to take the H2O in this case? Because you don't have a symmetrical triangle, is asymmetrical. H2O, you have to decide which one the H2O is going to attack, to the first carbon or to the second carbon. Is it always the second one?
It's the one with the less hydrogens, right?
the one with the less hydrogen. And how would you justify that? Is like the plus charge, because H2O is looking for plus charge, right? H2O is a nucleophile, is looking for plus charge. The plus charge is going to be more stable here because it's highly, that carbon is more substituted or highly substituted compared to this primary carbon. So if you bring the plus charge to carbon 2, you look like it's going to look like that you have a secondary carbocation, but if you bring it to carbon 1, it looks like that you have a primary carbocation. And definitely a secondary is going to be more stable. So the nucleophile is going to go to the attack to the second carbon, which is the secondary carbon, and the BR would stay on the first carbon. So when it's not symmetrical, you have to look for the plus charges being more stable in which, or basically more substituted carbon will take the nucleophile when you have this triangle or the positive charge that is shared in the triangle. The addition is going to be anti-addition again, because you have, how do we know it's anti? It's going to make your life easier if you say, whenever I see a triangle formed as intermediate, the addition is going to be anti-addition. If it's not a triangle, if it's just the open carbocation, it's a 50-50. So it's neither. You can say both, or you could say neither, because it can go from the top or bottom because it's open carbocation. It's not
just one.
triangle.
I'm sorry.
Yes.
One question. What do you mean when you say more substituted?
More substituted. So let me erase the writing here. So this carbon, okay, is more substituted than the other carbon 1, right? Carbon 2 is attached to 2 carbon. Carbon 1 is attached to 2 hydrogen and 1 carbon only. Or you can say that to higher order carbocation. So this plus charge, if it comes to this carbon 1, is going to give you primary. This is a primary carbon. This is a secondary carbon. The plus charge is more stable on the secondary carbon. So H2O would go and attach to the secondary carbon. Does it make sense?
Yeah, thank you.
You're welcome. And the OH and the halide is not going to be on the same carbon. So that's just, is less stable. The explanation also is demonstrated here. If you could, if this one helps you more, you can look at this explanation here. The plus charge is more stable on the more substituted carbon compared to the least substituted carbon. Oxymercuration, demercuration, that's a new reaction. What is oxymercuration, demercuration? It's an indirect addition of water. So in direct addition of water, you add H2O and you add H+. The addition was Markovnikov. The intermediate was carbocation. There was a chance for rearrangement. But for the for oxymercuration, demercuration, what is different? What's the benefit of oxymercuration, demercuration that we didn't have for direct hydration? What's the problem with direct hydration? Did you see any problem with direct hydration? Any disadvantage if you have direct hydration? In direct hydration, carbocation forms. And since carbocation forms, is going to there would be a chance for rearrangement. So if there is a chance for rearrangement, that is a problem. If you don't want any rearrangement to take place, you must do indirect addition of water. And one of the options would be oxymercuration, demercuration. So the benefit of oxymercuration, demercuration is that there would be no rearrangement. Addition is going to be Markovnikov addition. So when you make a flashcard for oxymercuration, demercuration, you need to know what are the reagents. These reagents are separated by numbers. And if they're separated by numbers, that means you get one product first, and then you're going to add sodium borohydride. So the reaction is two-step, is oxymercuration, and then reduction or demercuration. In oxymercuration, demercuration, you have Markovnikov product. See, hydrogen is added to carbon with the least number of, or least substitute or greater number of hydrogen, and OH is added to carbon with least number of hydrogen or more substituted. So you can say it either way, more number of hydrogen or least substituted. Less number of hydrogen or more substituted, it goes together. So in this reaction, the advantages you don't have to have sulfuric acid in the reaction, and it doesn't have carbocation rearrangement. So there is no carbocation rearrangement. So it's two-step reaction. So first is going to, alkene would react the mercuric acetate. Then you bring the sodium borohydride to the reaction mixture to bring a hydride. So basically hydride means like hydrogen with pair of unshared electrons with a negative charge, or you have hydrogen with the two electrons. You bring the hydride and you are going to reduce that. You're just going to remove the mercury from it and replace with the hydrogen. But just knowing the net result is addition of water. The final product is alcohol. The addition is Markovnikov addition. There is no chance for rearrangement. Those are a lot of information that can help you to answer multiple choice questions. Okay. Now, looking at the mechanism of the reaction, like step by step, what is going to happen when you have the mercury 2 acetate? Mercury 2 acetate is going to dissociate, and it's going to give you like mercury 1 acetate. It doesn't show you here, but I think that's going to help you more if you have HgOAc 2. This is OAc is acetate ion, is abbreviation for acetate ion. It's going to dissociate, and it's going to give you HgOAc plus OAc. Because OAc is negative, acetate is negative, so this must be positive. So the HgOAc with the positive charge is going to act like Br plus that you had in bromination. And the HgOAc is going to form a triangle with the carbon-carbon double bond. So if you look at this, or you add this to your notes, because it's not in the PowerPoint, it would dissociate. This part, it acts as a electrophile, reacts with the carbon double bond, and it would give you this triangle. As soon as you see triangle, what does it tell you? That addition is going to be anti-addition. So it's bringing plus charge into the triangle, then H2O comes in, and H2O is going to go attached to the more substituted carbon. So that would be the second carbon. When H2O comes in, doesn't bring any negative charge, you have a plus charge in the ring. So it requires additional step. The ring will break because this carbon already has 4 bonds. The ring has to break. Then you are removing hydrogen with the plus charge. And the net result for the first step is oxymercuration. You added OH and you add mercury to the carbon-carbon double bond. It's called oxymercuration. In the next step, when you bring your sodium borohydride, it's going to replace this part with hydride ion. So the next step is going to replace that with the H, and the net result is going to be addition of H and OH. So all the steps that you saw in oxymercuration, it was repeated from mechanisms that you saw before. So triangle is going to form, and then water would come from the opposite side. The triangle would break, and then you have a product after removing the H plus. Why do you have to be worried about removing H plus? Because when water comes in, it does not bring any charge. And if it doesn't bring any charge, negative charge, and you have a plus charge in the ring, then you have to worry about that plus charge, and you have to remove that plus charge. So the next step, you know, when it says like unclear mechanism, is basically less work for you. Somehow the mercury part is going to be replaced by hydrogen, so, or hydride. So you just remove this and add a hydride, add a hydrogen. So is also known as reduction. So oxymercuration demercuration or oxymercuration reduction is going to be same product as you were doing direct hydration, with one advantage, that there is no chance for rearrangement. Basically, this is formation of alcohol. Markovnikov addition is going to take place. So if you do have a CC double bond, H will add to this carbon and OH to the second carbon. This would always give you like a secondary alcohol, or maybe tertiary alcohol. It's not going to give you primary alcohol. So with this method, you cannot make primary alcohol, because the addition is going to be Markovnikov addition. So with the oxymercuration demercuration, you would get the OH on the second carbon. What happens if you want to make OH on the first carbon? How would you do this? Now, if you want to do, you add the OH to the first carbon, you must have a mechanism that goes through anti-Markovnikov addition of water. So for anti-Markovnikov addition of water, there is a new reaction, and that reaction is called it's called hydroboration oxidation. But for the hydroboration oxidation, I will let's just look at these examples before we go to hydroboration oxidation. So in the example, so if you see question like you have alkene, CC double bond, and you have these reagents. First of all, you have to remember that this reagent is for oxymercuration demercuration. You need to know that this addition is going to be Markovnikov addition, and the net result is adding H2O. And when you are adding H2O, it means that you add H and you add OH. Because it's a Markovnikov addition, H will add to the carbon with more number of hydrogen, and OH will add to the other carbon. Now, if you were adding, this case, you're adding, I'm sorry, alcohol. When you add alcohol, you're adding H. So if you had H2O here with the blue color, okay, if you had H2O here, you would have OH as a new example, because I didn't pay attention to this. So with the, if you had water, H will be added to this carbon with the more number of hydrogen, and OH will be added to the more substituted carbon. But if you, in this case, you're adding alcohol, okay? So when you add alcohol, you don't say oxymercuration, you would say alkoxymercuration. So in alkoxymercuration demercuration, just like oxymercuration demercuration, your addition is Markovnikov addition. But with this set, you're adding alcohol, basically adding CH3OH basically you add H and you add CH3O. H will add to one carbon and OCH3 will add to the other carbon. The product is going to be ether. So you're adding ether, just like adding alcohol. You had alcohol with the acid-catalyzed before. What is the advantage of using alkox immersion, demercuration, is that you don't have to deal with acidic solution again or sulfuric acid as a catalyst. Also, there is no chance for rearrangement. So there is advantages to this alkox immersion over adding alcohol with acid-catalyzed. Questions? No questions? A lot of reactions, you have to make sure to memorize the reagents and don't leave memorizing reagents to the last minute. Anybody who takes like exam 3 regrets that they should have spent more time on memorizing reagents, because if you know the reagents, you do well on the exam. So you have to know your reagents. And in order to memorize the reagents, the best thing to do is to make flashcards, write each of the topic for the name, title for the reaction, write what is the reactant. In this chapter, every time you write the reactant is alkene. What is the reagent and what would be the product? Then add like specifics. Is this addition Markovnikov addition or anti-Markovnikov addition, or neither? Is this addition syn addition or anti-addition, or neither? Is there chance for rearrangement, carbocation rearrangement? If there is no carbocation formation, then there is no carbocation rearrangement. Or if you have like a triangle, these are like some of the tricks that you can add, notes that you could add to yourself, your flashcards. If the triangle forms as the intermediate, there is no rearrangement, and the addition is going to be anti or anti-addition. Okay, formation of epoxide, that's another type of reaction. First of all, you need to know what is epoxide. Epoxide is a triangle, 2 carbon, 1 oxygen. That is epoxide. Okay, it's this epoxide is coming from CC double bond, which we call it like ethylene. So it's also known as ethylene oxide. So you have epoxide or ethylene oxide. How would you make this epoxide? You have to add oxygen to this. Where would you get that oxygen? Is that you use a proxy acid. What is proxy acid? What is hydrogen peroxide? Hydrogen peroxide has this formula. So carboxylic acid, let's say if I have benzoic acid, it looks like this. Okay. So I don't use the acetic acid all the time. That's a benzoic acid. Now, if I have proxy benzoic acid, how would be different is that you have your CO here. Then instead of having OH, you have OH. This is called proxy acid. Specifically is proxy benzoic acid, because we know what's the ring is coming from benzoic acid. So it's proxy benzoic acid. So if you have R group here only, it's called the proxy acid because it's general. But in this case, we have proxy benzoic acid. How stable is this? If you buy H2O2, they sell it to you in a brown container, right? Brown bottle. And it says to keep it away from heat and light. Why is that? Because this can decompose easily. It can change to H2O plus O2. It would be destroyed because this doesn't like to stay there. It comes out. Okay, it's going to escape or leave the molecule because proxy bond is not stable. Same thing here. This oxygen is not stable, is not welcomed here, so it wants to come out. And since we need oxygen here, a best candidate or best reactant to use the oxygen from is a proxy acid. There's an extra oxygen here that can serve as the oxygen we need for alkene. That's the easiest and simplest way for me to say it. When you are using proxy acid, this is basically oxidizing agent. It can provide oxygen because it has loosely bounded oxygen in the molecule. This oxygen can form the triangle, and then you have your epoxides. Okay. The benefit of this, your proxy is changing to carboxylic acid. After losing the hydrogen, it would be more stable. So your product here with the one oxygen is going to be more stable than the reactant that you had with two oxygen. So it kind of benefits the reaction because this bond is very weak bond between the two oxygen in a proxy acid, just like hydrogen peroxide that I had here as an example. Okay, formation of peroxide, is that a Markovnikov or anti-Markovnikov? Neither, right? Because you're not adding one to each carbon, you're just adding oxygen to the ring, and it's going to form a triangle. Is it going to be syn addition or anti-addition? Up to that step of formation of the epoxide, neither, because it doesn't, it's just one site. You don't have two things to add, it's just one thing that is being added. So you don't have to be worried about Markovnikov, anti-Markovnikov, you don't have to be worried about syn or anti-addition. Questions? Okay. Next reaction. Hydroboration oxidation is the next reaction, and this reaction is indirect addition of water. Okay. Hydroboration, borane itself is a Lewis acid because it's like electron deficient. Borane has only 3 bonds or 6 electrons. It doesn't satisfy the octet rule. It looks like a carbocation. Okay, so it's very reactive. So it can actually react, and sometimes it dimers itself. And when it dimers, it gets like a B2H6. Or when you use the borane, you have to use a solvent to stabilize it, like a tetrahydrofuran or something to stabilize borane. Borane is very reactive. It looks like a carbocation because it has only 6 electrons. So it's a electron, it likes electrons. So is a electrophile, strong electrophile. They use the tetrahydrofuran or THF. This is just the solvent that is going to stabilize the BH3. So do not bring and add to one of the carbons, please. Okay, it's just the solvent. This is just the solvent, and is stabilizing BH3. The net result of this reaction of the hydroboration oxidation is addition of water. You're adding H and you're adding OH. The addition is anti-Markovnikov addition. Okay? The addition is anti-Markovnikov addition, and the addition is going to be a syn addition. Both H and OH will add from the same side. So if you do direct hydration, you get Markovnikov addition. If you do hydroboration oxidation, it gives you anti-Markovnikov, and this is the only case that you can get like a primary alcohol. You cannot get from primary alcohol from direct hydration or from oxymercuration, demercuration. But with hydroboration oxidation, you would get the anti-Markovnikov addition. And another trick, or another like a memory trick for you, if your reaction involves H2O2, anytime that you see in the reactions you have H2O2, you had that for in anti-Markovnikov addition of HBr when you bring like a peroxide. So whenever you have a peroxide used in the reaction mixture or as a reagent, the addition is going to be anti-Markovnikov addition. It's not written in the books that you're going to have like anti-Markovnikov addition if you have H2O2, but you have seen it a couple of times. Anytime there is a peroxide, the addition is going to be anti-Markovnikov. So when you see this H2O2 in the reaction mixture, you know the addition is going to be anti-Markovnikov. H is added to carbon with least number of hydrogen, and OH is added to the primary carbon with more number of hydrogens. So in the hydroboration, for when the borane comes in first, is basically kind of forms a bridge here. Both BH2 and H are added from the same side. That's in the first step of the reaction. So H is going to attach to more substituted, and BH2 would attach to the least substituted carbon. Because in this case, the hydrogen with the electron is acting as a nucleophile. So not nucleophile is added to the higher substituted carbon. On the next step, when you do oxidation, you remove this and add OH. That's where you're bringing H2O2. So you end up having OH on the first carbon, or a primary alcohol. So you can read these from the PowerPoint is provided in the chapter as well. It has more explanation of the steps. So the final product is going to be alcohol, and specifically in this case is going to be primary alcohol, or anti-Markovnikov product rather. So looking at the overall reaction, with these examples that we have here, you have asymmetrical alkene, but there is no rearrangement, okay? If it's asymmetrical, then you have to worry about, is it Markovnikov or anti-Markovnikov? There is no rearrangement, and the addition in this case is going to be anti-Markovnikov. And how do I know it's anti-Markovnikov? Because I see this H2O2. It goes back to a stability. Again, it goes back to more stable intermediate. But overall, if you're looking at the overall reaction, I see H2O2. It has to be anti-Markovnikov addition. You have asymmetrical example here. So we know that this reaction mixture or reagent mixture or set of this reagent translates to adding H2O and adding H, adding OH. Because of the H2O2 is an anti-mark, okay? And because it's anti-mark, we are going to add the H to this carbon and OH to the first carbon. So when you see a reaction or you study reaction, what you need to know from the reaction, what would be the product is like based on the reagent that you're adding. This reagent represents addition of water, is indirect addition of water, but the addition is anti-Markovnikov addition. So you need to know which one takes the hydrogen and which one takes the OH. You have another asymmetrical one. We know that this reagent is adding water. H will add to the more substituted, and OH will add to the least substituted. Both of them would give you a primary. This demonstration, basically, it says that there is no methyl shift, there is no hydride shift, there is no rearrangement. For hydroboration, oxidation, there is no rearrangement. For oxymercuration, demercuration, there is no rearrangement. But for direct hydration, there is a rearrangement. See how many more reactions we have. And okay, I'm not going to finish the chapter, but let me see a good point for, I think we end up with the summary. Let's talk about the hydrogenation. Hydrogenation is addition of hydrogen, addition of 2 hydrogen. So that's hydrogenation. Make sure you don't add just hydrogen. The hydrogen needs to be added with the catalyst. So you would add hydrogen with platinum, palladium, or nickel, and all of them can work. And when you add the C here, it means it just reduces the activity of the catalyst, so it makes it more mild or moderate catalyst. What's the net result? Addition of 2 hydrogen, 1 hydrogen to first carbon, another hydrogen to second carbon. Is this Markovnikov or anti-Markovnikov? Or neither? Markovnikov, anti-Markovnikov, or neither?
Neither.
Neither, because there is no nucleophile electrophile. Both of them are identical, so there is neither. And is this syn addition or anti-addition? In this case, it's actually a syn addition, because addition of hydrogen happens at the surface of the catalyst. So when you use a solid catalyst here, hydrogen is going to attach to the H2 would attach to the surface of the catalyst that you're using. And then the carbon-carbon double bond comes and acts at the surface. So hydrogen would add to the first carbon, kind of opens the bond, and then the second hydrogen attaches from the same side because they are already embedded on the surface of the catalyst. It doesn't react in the reaction mixture. It doesn't in the space. It happens at the surface of the catalyst. Since all hydrogens are on the same surface, the alkene comes in and gains the hydrogen from the surface, is going to be added from the same site. So this addition is known as the syn addition, addition from the same site, is not anti-addition. Summary of the reaction. Of course, these slides are going to be helpful for you to prepare your flashcards, but please remember, when you are preparing your flashcards, to include if the addition is Markovnikov, anti-Markovnikov, or neither. Know the reagents, and possibility for rearrangement. Include that because it's going to help you. So you have acid-catalyzed addition of water, acid-catalyzed addition of alcohol. You have oxymercuration, demercuration, which is indirect addition of water. Hydroboration oxidation is indirect addition of water, addition of halogen, and addition of hydrogen. So okay, I usually include this diagram in a test and or exam or both. So just be prepared to see something on the quiz or on the test or both. There would be like numbered. What are the numbers? And then, you know, what are the reagents, basically. memorize
Yeah.
all the reagents.
Can you give us the numbers right now? Or no?
It doesn't matter. Like if you know the reagents, it doesn't matter which numbers they are. So you would get the whole diagram in quiz or in exam or in both. So just memorize the reagents. So if you were, if this was a number 1, what would be the reagent? So you would write here 1 is going to be addition of HBr, so it's going to be HBr. And then this is, what type of addition is this? Is it Markovnikov or is it anti-Markovnikov? Because is a anti-Markovnikov, then is not the direct addition of water. So you want to make sure that you know this reagents. That would be like, if this is 2 would be this one. And then formation of triangle. From this going to triangle like this one, if that was 3, you have it here. The reagent is going to be proxy acid. You're looking for the reagent. And then in this case, let's say if this is 4, you're adding Br and you're adding OH. So it's going to be Br2 and then H2O, both of them. Addition of alcohol, and it is addition, the addition is Markovnikov addition. So it can be alkoxy mercuration. You have 2 chances. Addition of direct addition of alcohol with the acid, or alkoxy mercuration, demercuration, both of them would work. Direct addition or oxymercuration, demercuration. So you have both chances. Oh, for 1 was not HBr because I didn't see this Br here. You're adding Br2, right? For 1 is a Br2. HBr is used here. So if you go through like the slides, you can complete the, write the reagents for all. You have that in the homework assignment. Okay, enough reactions. Let me stop recording.